In conclusion to the first point on how we determine valency using the charges, and I want us to have this table together where we shall have different groups and their valencies from the various ions that are formed. So in group 1, we have lithium as an atom, we have sodium, and we also have potassium from the first 20 elements. Lithium as an atom forms lithium ion, and now that we have only one charge, as I shown you last time, we only have one positive charge. So though we don't write the 1, we usually omit the 1, so it remains as capital L, small I, and a positive. The valency is 1. Sodium forms sodium ion, again with the valency 1. Now that the positive charge is just 1, so it lost only 1 electron. Going to potassium, again it lost only 1 electron, remaining with 1 extra positive charge, so valency 1. And remember, we are checking on those elements that are among the first 20 elements in the periodic table. So then we go to group 2. Remember, group 1 are the alkali metals. Group 2 are the alkaline earth metals. So among the first 20 elements, we start with beryllium as an atom. Remember, we don't join the letters, so let us have a safe space. So forming beryllium as an ion, so we take the valency to be 2, valency 2. We don't write the charge, it remains as a whole number. Next we have magnesium with a capital M. Remember, capital M has corners, forming magnesium ion. Again, valency is 2. Next, in group 2, we have calcium, forming calcium ion, again with the valency 2. From there, we go to group 3. This side we have group 3, and when I write it as this 3, it will be wrong. I have written it to just remind you that when you're writing the groups, we don't write them with the normal natural numbers. Instead, we use the Roman numbers. So never forget, because if you use the 3, it will be wrong. So instead, always remember that we use the Roman numbers. So in group 3, among the first 20 elements, we begin with boron, which forms boron ion with the valency 3. Next we have aluminium, forming aluminium ion with the valency 3. Again, remember, we don't indicate the charge when we are writing the valency. Valencies are normally whole numbers. From there, we have group 4. Group 4, we have 2. Among the first 20 elements, we have carbon, forming carbon as an ion, and remember these ones are the metalloids. They can behave as nonmetals and they can also behave as metals. So when they behave like metals, they end up with 4 positive, so valence 4. When they behave like nonmetals, they will gain 4 electrons, so 4 negative, but still with the valence 4. Then we have silicon, which is also among the first 20 elements and in group 4. Again, silicon can gain 4 or lose 4. So again with the valency 4. Then we have group 5. Group 5, we have 2 of them again. We have both nitrogen, which can gain 3 electrons, so with the valence 3. Then we have phosphorus, which can gain 3 electrons with the valence 2, I mean 3, with the valence 3. But phosphorus can also behave in an unstable way and form phosphorus 5 positive, so lose the 5, though this one is very unstable. The one that is stable is this one where it gains 3, so but it can also lose, and by this time it is unstable, so this time it has valency 5. So but the most common and the one that is stable is the phosphorus that has a valency of 3. So we continue with the group 6, but before then make sure that you're writing good notes. Next we have group 6. Elements. In this case we have 2 among the first 20 elements. We have oxygen as an atom forming the oxide ion with a valency of 2. Then we have sulfur forming the sulfide ion again with the valency 2. Then we have group 7, the halogens. We have the first one among the 20 elements. We have the fluorine atom. When you're writing capital F, remember we have a corner up here, and this tail should not pass the vertical line. So the fluorine atom forming the fluoride ion, and the valency is 1. In actual sense, we should write the fluoride ion with 1 negative, but we said earlier on that if we write this one and a negative, it is just a repetition, because even without the 1, how many negatives are these? Just 1. So you see 1 negative and just a negative, even this one is 1 negative. They are not 2 negatives, just 1 negative. So we avoid the 1. So the fluoride ion is written as capital F, and a negative is just 1. Then from there we have chlorine atom forming the chloride ion, with just a negative, and so the valency again is 1. When you're writing small l, it should not have a corner down here, like we should not have small l with a corner. This one is capital L. So if you write chlorine with an L that has a sharp corner, it will be wrong. However small the L is, if it has a corner, it will be very wrong. So you should instead have an L that has a rounded corner. Now that you are not printing it, I see when they are writing it, sometimes they just write it as like they are writing a letter I. So, but when you're writing it using your hand, always have the L with a rounded corner here. However small, however big, if it has a rounded corner, it will be a small L, just like we said about M. If you write for magnesium with an M with rounded tops, it will be a small m and it will be wrong when you be writing the formula for magnesium. So let us now go to group 8. For group 8, these are the noble gases. The noble gases, these ones have a valency of 0 because they do not gain, they also do not lose. So they neither gain nor lose. Neither gain nor lose. So they do not have any charge. They do not have any charge. So for these ones, when you're writing their atoms, for example, when you write helium atom, you write neon as an atom, you write argon as an atom, so there will be no charge because they just remain as atoms. They will not form ions. In fact, in the periodic table, there is a common question that asks the learners to determine the group that has monoatomic gases or that has monoatomic elements. It is group 8, where we have the likes of helium, neon, argon down the group. So that was one way through which we are able to determine the valencies of different elements in the periodic table. So I hope you can see and write good notes. So we continue with the next method of determining the valency in our next lesson. Before we begin the second way of determining the valency, I don't want us to forget that we also have radicals that we also use in the writing of chemical equations, and we also require to know how their valencies are determined. Radicals, as we said earlier on, they are a group of atoms that react as a unit. They react as a unit, and they usually have a net charge written on top of the atom. So even for these radicals, we also needed to determine their valencies. And in fact, for these ones, it is very easy, just like we did for the single elements. So for radicals, they are those that has a valency of 1. And these ones include the hydroxyl ions. Other people will call it the hydroxide ions. When you look on the net charge, on top here, it is just 1 negative charge. So we say it has valence 1. We have another one that also has a valency of 1, the ammonium ion. It has a 4 down here. Let me write it clearly. This is a 4. Again, on top here, it just has 1 positive charge, so the valency is 1 also. We also has another one, very commonly used, the nitrate ion. So it has a valency of 1 as well. This is the hydroxyl ion or the hydroxide ion. This one is the ammonium ion. That one. This one is the nitrate ion. So for each one of them, it has a valency of 1. You just look at the charge and then you determine the valency. Before we move to valency 2, remember we also have the hydrogen carbonate, also with a valency of 1. It is known as the hydrogen carbonate ion. It also has a valency of 1. We also have the hydrogen sulfate. Let me write it well. In the writing of chemical symbols, you always avoid having them attached to one another. So hydrogen sulfate ion with a negative ion. The hydrogen sulfate ion again has a valency of 1. So those are radicals. They are usually a group of atoms. In each case, we have more than 1 atom combining, and they always react as 1. Reacting as a unit means they react as 1. Next, we have those radicals that have a valency of 2. Radicals with a valency of 2 include the carbonate ion. We usually check on this number that is on top here. So this one has a valency of 2. Remember, we don't indicate the charge because valency is just a whole number. Then we have the sulfate ion. Again, we check on this number and then we omit the charge, so just a whole number. Then we have the sulfite ion. Again, we look at this number, so it has a valency of 2 as well. Then we go to those radicals that have a valency of 3. Those include the phosphate ion. This one is the phosphate ion. Again, we check on this number, so we say that it has a valency of 3. So remember, this is the carbonate ion. This one is the sulfate ion, just in case you didn't get the name. This one is the sulfite ion. This one is the phosphate. That is the phosphate ion. These radicals are very important. One, when you're writing chemical equations, and again, especially in the practical bit of it, when you are dealing with qualitative analysis in the use of ammonia solution and the use of sodium hydroxide solution, when you are determining which compound was in a certain salt, you are required to use the symbols. for various radicals sometimes. So for example, you put ammonia solution, you put a few drops of sodium hydroxide solution, and then maybe depending on the kind of an inference that you get, the kind of observations that you get, maybe you see that it is a sulfate ion that was present. You don't write the name, you instead use the symbols. So it is very, very important you know how the symbols are written for various compounds, and again their valencies, in case in any given chemical equation you are required to write you are required to use them in the writing of chemical equations.